Welcome to today's special feature, where we delve into the details behind an engineering marvel that has gripped the nation. 5 enterprising young men and women set out to build a 2-bladed wind turbine of immense quality to achieve maximum power as a stated tip speed ratio. Self-starting, as light as possible, a horizontal axis rotating anti-clockwise. I bet that's piqued your interest. Let's see how this motley crew fared. I was joined by Hermione Modi and Webcast Punja. So, it was a very complete design project. Let's see how they went through the design process. So, I'm at Imperial College London with Rikesh Punja. Now Rikesh, I must ask you a question. How did you go about designing the aerodynamics of your wind turbine?
Well, choosing the tip speed ratio, TSR, was the first step in our design process. Optimum TSR for full-scale industrial wind turbines tends to be between 4 and 6. But since we have a smaller wind turbine of only 800mm tip-to-tip diameter, we chose to go on the lower end of the scale for about 4.5. So the next stage was choosing the aerofoils for our wind turbine. The Reynolds number for the flow was of order 10 to the 5. So we had to choose aerofoils with maximum CL to CD ratio at this Reynolds number. From these constraints, we found that the best aerofoil for us was the SG6043 series.
Well, I'll take you through the aerodynamic calculations we did in order to design our wind turbine. Having decided on our TSR, we worked out our angular velocity as 120 radians per second, based on the maximum wind speed of 12 meters per second using equation 1. The actual velocity seen by the wind turbine varies along the length of the blade, so in order to keep our angle of attack at 8 degrees, which is the value for optimum CL over CD, we need to introduce a pitch angle or twist to the blade. Using wind turbine geometry with figure 1, we get equation 2. Now rearranging equation 2, we can get the twist angle of our blade at a distance r along the blade from the edge of the nose cone. Based on Bet's theory, to maximise CP, the value of A1 in the equation should be approximately a third. From theory, we found that for maximum power, the optimum theoretical planform area for a single blade was 0.0208 meters squared. The process of working out the chord lengths was an iterative one. We started with an initial value for our chord length at the tip and used a 1/r relationship to work out the chord lengths up to the maximum chord length. From there, we used another 1/r relationship to taper to the root. This process was repeated for different starting values until our blade had the optimum planform area we previously calculated.
Hello everyone. I did the structures calculation for a wind turbine lab. The main aim of this process was to work out the tensile strength and the compressive strength to make sure that they're within the critical limit of ABS plastic, so they're less than the yield strength.
We started with calculating the centrifugal forces along the blade. The large mass of a wind turbine and the relatively high angular velocities can give rise to significant centrifugal forces. It's maximum at the tip where the angular velocity is maximum. For convenience, we neglected the relatively small twist of the blade cross section and assumed that these bending moments are aligned with principal axis of the blade. There were a few other assumptions that we made during the process. We decided to split the blade into elements, assume that for each element the loading and the rigidity EI are going to be constant. We then worked out the bending moment. As you can see, the lift forces causes the flap-wise movement at the root. The tangential forces would cause tangential movement at the root. So, using the above equations, we worked out the bending moment as 3.94. Through careful research and reading of scientific papers, we came up with this formula for moment of inertia of an airfoil cross-section about the z-axis, which is given by the upper and the lower surfaces. Having worked out the moment of inertia and the bending moments along the blade, we then went on to calculate the direct stresses in the direction normal to the blade and tangential. Having worked out the direct stresses, it can be concluded that they are well below the yield stress of the material, thus the blade would not fail from bending.
I then spoke to Colin Chan, who supervised the CAD modelling of the turbine.
As soon as we were set with the aerofoil and design TSR, I began tinkering with PTC Creo to try and figure out which feature was best for replicating a blade. And I found out that the best one to use was a blend function and blend a few aerofoil profiles together, because the aerofoil cross-section changed in chord length and in angle of attack, as we progressed along the blade. Near the blade tip, we swept and rounded the blade so as to avoid a sharp corner. And at the blade root, we attached it to the nose cone using an extrude feature. And the nose cone was made using a simple sketch and revolve feature. And the second blade was made by duplicating the first blade using a mirror and rotational mirror option.
Mr. TJ spoke to me about Group 13's manufacture and design of the hub and nose cone.
Well, we knew we wanted a lightweight, high-performance hub. So we had to go straight to the basics. We went first for shape. Someone suggested a circle first. However, all the force would be translated through the grub screw. This was not an ideal situation. So we went for a shape with corners, as even though there would be a stress concentration at the corners, it would make sure there would be no slipping and all the force could be translated through different points. Now, the more corners you have, the less the stress concentration. So obviously we went for a high corner shape. You know what that shape was? It was a hexagon. No, let's go for an octagon. So now we had the shape. We wanted to make it even lighter. We put slots into 7 sides, managed to keyway slot, so that way we didn't have a lacking of material at that point. Because the important thing is that our hub held together and made sure it was able to translate all the force we needed.
Do you want to know how we manufactured this amazing hub? I'll tell you how. First, we started off with a cylindrical block of aluminium. Went to the centre lathe and faced it off first. Next was to use the centre lathe again to cut the aluminium down to the correct length and the correct diameter for our hub. Then we used a tailstock to bore the 8mm hole for the hot shaft the hub would sit in. Next we went to the milling machine. On the milling machine, we turned our cylindrical block into the octagonal block, octagonal hub that we designed. From here, we did this by using the cutting tool to cut a plane, rotate the vise 45 degrees, cut another plane, and until we had the 8 faces. Next was to use a slot drill to create the slots in the same fashion that we did the planes. After that, the last process on the milling machine was to just use a drill to make the hole for the grub screw. The last process we used was going to the broaching machine to make the keyway by removing material using a hydraulic pump.
So, after all that hard work, Group 13 then tested their turbine in Imperial's Honda wind tunnel. Guys, how'd you get on?
So to ensure that our turbine performed how we wanted, we tested the various amounts of wind speed. We tested at 4, 6, 8, 10 and 12 meters per second. At 4 meters per second, our blade cells tied and it went fantastically. However, unfortunately, it did break at 12 meters per second. It broke right at dovetails, which was quite an unforeseen result. We expected if it was to break anywhere, it'd break right at the root. We believe that the breaking at dovetail occurred because it was because of our positioning and the stress concentration at the dovetail. However, we did have a great performance between 6 and 10 meters per second.
Yeah, between the speeds of 6 and 10 meters per second, our blade actually performed pretty well, and it achieved a maximum CP of 0.24 and a TSR of just under 6. However, at this 10 meters per second speed, we did see quite a lot of significant oscillations on the blade. Here's a few clips of how our blade performed.
At 12 meters per second, Group 13's blade broke, but resonance was clearly visible at 10 meters per second. In future, it will be worthwhile designing for the avoidance of flutter, so their turbine would not be loaded at a natural resonant frequency, estimated using perhaps a lump mass idealization. The addition of downstream pointing wingtips to the existing blades should reduce induced drag, minimise tip losses due to training vortices, and hence increase the power produced, and sweep and cant angles should help to maximise this effect. Their design TSR was 4, whereas they actually achieved just under 6, so further inspection of the theory, assumptions and calculations will be needed, as this led to an increased speed of angular rotation. The shape and position of their dovetail joints should be reassessed for greater structural integrity, as this is where they saw their blade break. They should also be aware of the limitations of BEM theory and the subsequent wake swell losses. Well, I think I've reached my bed's limit for today. I have to say that was a fascinating story. Thank you very much to Group 13. Just remember, guys, It's not about the size of the force, it's the angle at which you apply it.